Today we're going to be looking at uniform acceleration. Now, acceleration is essentially how fast velocity is changing over a set period of time. If an object's velocity is increasing or decreasing, there is in fact acceleration. We noticed already on the graphs when you had a velocity of 12 meters per second, for example, that was continuous, it was a uniform velocity, you had no change in acceleration, you would have an acceleration value of 0 because there was an initial value of 12, a final value of 12. And so if you subtracted it, you would have 0 out of whatever time you took to do that. So acceleration is just the change in velocity in a specific change in time. And again, it's whatever your final velocity value is minus your initial value. That's going to give you your overall acceleration. Your units for acceleration will be meters per second squared, and that's how we will normally express our values. And by normally, almost always. In physics, positives and negatives only indicate direction. And we've mentioned this before. But one thing we haven't mentioned is if you have a negative acceleration, that does not necessarily mean an object is slowing down. If you were already traveling, say, west, and you were increasing your velocity in the western direction, you would be having a negative acceleration. Your acceleration would be accelerating to the west. It would be increasing over time. Your velocity would be increasing over time, so you would have an acceleration, but it would be a negative acceleration because it's moving to the left or moving west. So it doesn't necessarily mean that the object is actually slowing down. So just because you have a negative acceleration does not mean the object is slowing down. It's only telling you in which direction there is acceleration. A big difference right there. If the acceleration and the velocity are in the same direction, the object will speed up. So that was a perfect example. If you're moving west and you were increasing your velocity west, that means that both directions, west for the velocity, west for your acceleration, that means that the overall speed of that object will increase. Now, if you were traveling west, but you were accelerating to the east, well, now if you have opposite directions, it will now cause the object to slow down. So you could have a positive acceleration, but you have a negative velocity. You could actually then be decelerating and you would begin to accelerate in the positive direction. And even velocity-wise, well, once you hit 0 velocity, so you'd be traveling this way, slow down, and then stop, and then you would continue accelerating to the right, and then begin to increase your velocity to the right. So it starts off by slowing down and then speeding up in the opposite direction. So objects speed up when acceleration and velocity are in the same direction. Objects that slow down happens when acceleration and velocity are in the opposite direction. So, for example, a car is coasting backwards downhill at a speed of 3 meters per second when the driver gets the engine started. After 2.5 seconds, the car is moving uphill at 4.5 meters per second. What is the car's acceleration? And so first of all, what we can say is we need to denote a couple things here. Let's call uphill the positive direction, and let's call the downhill the negative direction. All right, so it's initially going at negative 3 meters per second. And so we can have an initial velocity of negative 3 meters per second. Its final velocity is going to be 4.5 meters per second. So just be aware, you want to make sure that what's going on with your directions here. So in this case right over here, if it's negative 3 meters per second because it's going down, over here we have it going up, so it's going to be positive 4.5. And our final value of the car's velocity was 4.5. The initial was negative 3. So it initially started going down, then it started going up afterwards. And so if you wanted to say, well, what is a change in velocity? Because in order to find acceleration, which is what we're looking for, you first need to figure out, well, what is the velocity, the change in velocity, and then you do that over that 2.5 seconds to figure out what the acceleration is. So if we just even go over here, what is acceleration? That is a change in velocity over time. That's going to be your final velocity minus your initial over time. And that's going to be your 4.5 minus the -3 over 2.5 seconds. And add the opposite. So that's going to give you 7.5 over 2.5, which gives you an acceleration of 3. And if we look 2 sig figs, 2, so 3.0 meters per second squared. And then we could also say uphill. Again, positive denoting that it's moving upwards. So we can also just kind of mention it right over there as well. Do not forget your units, sig figs, direction, all of them when you're dealing with vectors. And acceleration is indeed a vector. The next example, a car slows from 22 meters per second east to 3 meters per second east at a constant rate of 2.1 meters per second squared. How many seconds are required before the car is traveling at that 3 meters per second to the east? And so, well, let's take a look first at the formula. And the initial formula is acceleration is change in velocity over time. We're looking for time. So if we want to solve for time, what we should do is we swap these over here. And we're going to have time is equal to change in velocity over acceleration. So we were already given the acceleration. The acceleration is 2.1 meters per second squared. It also is mentioning that the car is slowing down. And so, first of all, if the car was going 22, it's now going 3 at the very end there. We can mention that too. We can say that our initial velocity was 22 meters per second east, and our final velocity is only 3 meters per second east. We looked up over here before saying that if the object is slowing down, which is what this example is stating, the acceleration and velocity are in opposite directions. So with that being said, if our velocities here are both to the east, so even our final velocity is still to the east, that means that our acceleration, this 2.1 meters per second squared, is actually going to be to the west. And so if we were to write that down, that's going to be some type of negative value, right? It's not going to be positive 2.1. We're going to have an acceleration of negative 2.1 because it'll be moving to the west. It's opposing this velocity. The only way in which you're going to be able to decrease your velocity with an acceleration is in order to go the opposite way. Imagine your object is traveling at 22 meters per second, but it's slowing down. The only way it's slowing down is if it's actually accelerating in the opposite direction. And so again, the way to denote that is with a negative. So it's accelerating to the left or accelerating west. And that's represented with this negative in front of the 2.1. Now that we have all of our values, we can just plug it into this formula right over here. That's final minus initial over acceleration. Our final is 3 minus our initial. So 3 minus positive 22 over negative 2.1. What's also good too, you want to make sure that your value, your final value is going to be a positive value, because if we're dealing with time, we want to have a positive amount of time that this is going to transpire over. You can't have a negative amount of time. Going back in time to figure out how far the car goes, no, it doesn't work. If we just work this out, we will get 9 seconds. And so again, 2, sig figs all the way along. Our units, there's no direction with time, and that ends up being our final value right there, time being 9 seconds. Remember, if you're punching this in on your calculator, this whole thing on the top is all in brackets. You could also do this in your head as well. All right. Let's take a look at some of those other kinematic equations, because there are a variety of them and each one is useful for different questions. There are often a number of different variables that you can have. We have 5 different variables that we often operate with, and often when solving these types of problems, I will write the following on the side of the problem each and every time, so I stay consistent. And it looks kind of like this. I call it TAD VV. It's what is the time, what is the acceleration, what is our displacement, what is our initial velocity, and what is the final velocity. And so these are the types of questions to ask. Often in a question, 3 of these will be given or can be easily found right away, and then you'll be looking for the 4th unknown value. And then often the 5th one is not even given. And so based on that information, with one of these pieces of information not given at all, and 3 of them given, you're able to solve for the 4th one based on the different equations that you use. And so if you notice and you look at your formula sheet, there are going to be different formulas, each one where there's going to be at least one of those variables missing from this list right over here. And again, that's done in such a way so that you can actually use the proper formula with the information that's given within the question. Anyways, there are several different kinematic equations, very useful when solving problems. These new equations can be used along with all the other equations that we've already used. So we've already taken a look at average velocity. It's a little different than the change in velocity. So if you're looking at average velocity right over here, this equation is just another way of calculating average velocity. It's similar to actually just calculating the average of a number. You just add the 2 up, your initial and your final, and you divide by 2. And that should kind of make sense as well. If you were to logically think about it, if you were traveling first at, say, like nothing at all, 0 meters per second, after a while you're traveling at 10 meters per second, well, throughout that whole time, you averaged 5 meters per second, whatever that might look like over that time period. So if you have your final and your initial right over there, that would be what your average would look like. Your second equation. To find this equation, we take equation 1 and we combine it with our average velocity, so the change in displacement over the change in time. And what we end up getting is the following here. We say, okay, the same idea right over here, we're just manipulating this one too. We're saying if we want to find what is the change in displacement, all we're going to be doing is multiplying by a change in time on both sides of this equation right over here. So we're multiplying by time over here, multiplying by time over here. These will cancel, leaving us with change in displacement is equal to time multiplied by your average velocity. So we have change in displacement is equal to time multiplied by our average velocity. And so this average velocity over here is just plugged in to this part right here. So this average velocity is still over here, and then multiplied by your time. And that's another way to kind of look at the same problem here. So if you were to think this through logically for a moment, you're saying, how far did I travel displacement-wise, right? So it's not your total distance, but it's like you traveled from point A to point B, and it could have been in a big circle like this. That doesn't matter. What ends up mattering is where did you start and where did you finish? So say you started right over here and you went all the way around and around and around and traveled this entire distance and landed up right over here, then all it would be from there to there then, your initial point to your final point. So depending what that's going to look like, what is your change in displacement over that? And so if you were to actually calculate that, then just remember what's your final value minus your whatever your initial value was. And that's going to give you your point there. All right. Anything else with this one? Velocity average. Yeah, so calculate the average velocity, multiply it by the time. So going back to this one here, say that for some of this time you're going really fast, some of you are going really, really slow. In the end, it really doesn't matter. All that really matters is what is your average velocity over that time frame. So you could have been going really fast for some of that. You could have been going really, really slow for another part of it. In the end, you're saying, well, what is your average velocity over that time frame? And then you just multiply it by your time. And this would be similar to when the graph was drawn from before. So let's turn this into a graph just for a little bit here. And say we had the velocity time graph where it started off, let's say it starts at 0 right there. And off it goes to a certain point here, say like 20 meters per second in 10 seconds, right? And you're saying, well, what is your displacement? Well, remember, to get from your velocity time graph back to your displacement time graph, all you're doing is finding the area under the curve. which is just base times height divided by 2, right? Base times height divided by 2. And the height, if you look at the height, what is the height? The height is just your final value here minus whatever your initial value is at the bottom there. So your final velocity minus your initial velocity. So the change in that amount over that time frame multiplied by the time right over here. So that's really what's going on. And then you divide it by 2. And you're going to be getting the area under the curve. And that's why we said before there are like kind of 2 different ways to calculate your average velocity. And this was one of them. And we had the other one that was shown from before too. Sweet. All right, moving on. Which would have just been your change in displacement, final minus initial over time. So looks a little bit different than that. Anyways, that was just a quick little review from before. Moving on to this. Example. An object has an average velocity of 13 meters per second north and initial velocity of 2 meters per second north. What is the final velocity of the object? So let's start with what we do know. We know that our average velocity is equal to the initial plus the final divided by 2. If we're looking for a final velocity, I like to manipulate this formula. So I'm going to be multiplying by 2 on both sides of the equation. I'm going to get our average velocity multiplied by 2 is equal to our initial plus our final. And with our one last step here, we're going to be subtracting the initial on both sides. And then instead of writing it equal to the final velocity on the right side, I'm going to just put it to the left side. So all I'm doing here is subtracting VI on both sides. And we're going to have 2 times our average velocity minus our initial velocity. So we're going to plug in our values up here. Our average velocity was, it says 13 meters per second. So it's 2 times 13 minus our initial of 2. So we're going to have 26 minus 2. We're going to get 24 meters per second. We have our units, we have our significant figures, and we just need a direction. It will continue to be north. It's a positive value. And that is how you go about solving that particular question. So just be aware of what you have. In this question, we knew the initial, we knew the average, and we were looking for the final. So we went to the formula that we had from over here, and then just manipulated it and then plugged in our values. Example 2, a ball has an initial velocity of 3 meters per second east. It travels 4 meters to the east while accelerating to 11 meters per second east. So it travels 4 meters east while accelerating to 11 meters per second. So it starts at 3, it goes to 11 meters per second. How long does this take to do? Because we're only traveling over a small period of time right over here. In this case, we have a displacement. It travels 4 meters, right? So we have our displacement right over there, so we can write that down. Our displacement is 4 meters east. We have our initial velocity of 3. We also have our acceleration, which is in the same direction here, so we know that's our final velocity. While accelerating to 11 meters. So sorry, we don't know what our acceleration is, but we do know what our final velocity is here. So our final velocity is 11 meters per second to the east as well. So to the east, to the east. All right, based on this information, we have final, we have initial, we have displacement, and we're looking for time. So if we look to this formula here, we have final, we have initial, we have time, and we have displacement, and we're looking for time. We just have to rearrange this formula a little bit so that we can actually solve for time. So start by writing that formula out again. Our displacement is equal to our initial velocity plus our final velocity divided by 2, all multiplied by our change in time. And now we're going to isolate this variable by bringing everything over to this side from this side right over here. And luckily everything is multiplying the time. So we are just going to be bringing this over by multiplying both sides by 2. So I will just show the steps one at a time. VI plus VF. Again, this is still in brackets over here, so make sure that it stays in brackets right over there. And then the next step is we're going to be dividing both sides by VI plus VF. And so what we end up getting is 2D on the top and VI plus VF on the bottom. And again, we'll leave it with the brackets there. So I divided both sides by that to get what our time is. Now we just have to plug in our values. So we had our values over here. We manipulated our formula to solve for our unknown variable. And now we're just plugging in our numbers. 2 times 4. And on the bottom here, our initial plus our final. 3 plus 11 is 14. 8 over 14. Which gives us a time of 0.57. So if we had this 571, that rounds to 0.57 with 2 sig figs, our units. And that solves that question right over there. So it doesn't take very, very long to do so, to get from a velocity of 3 to 11, especially if it's only happening in a time frame of 4 meters. It does it very, very quickly at 0.57 seconds. So if you wanted to, you could even actually calculate what your acceleration would be then, because you do have all the information that you would need. You have your displacement, you have your initial and final velocity, you also have your time rate over there. So if you really wanted to, you could have done that. You could have used the acceleration formula right over here, your final minus initial, divided by your time. So it was final minus initial, 11 minus 3, 8 over 0.57. You're looking at something probably 14, 13 meters per second squared, so quite fast, faster than the acceleration due to gravity. So again, just an estimate, but you could actually calculate what that would look like exactly. All right, final page here. Speaking of gravity and what the acceleration of gravity is, it is 9.8 meters per second squared down. And so an object is said to be in free fall when only the force of gravity is acting on it. So if you were to drop this pen to the ground, gravity is going to be accelerating this pen down to this table at 9.8 meters per second squared. When we solve these types of problems, just keep this in mind. We have to assume that there's no air resistance. Otherwise, it becomes very, very complicated. We would have to use calculus, which none of you, have actually studied that just yet. So it's not like it's a complicated idea, but it's just that nobody's studied that just yet. And so we will not be using air resistance for calculating these problems out. So clearly, our values would be a little bit different than what you would see in the real world. But it at least gives us a nice picture of approximately what it would look like. Secondly, the acceleration due to gravity is the same at all locations on the Earth. And again, that does vary small amounts, but we will just have that assumption too. We will be assuming that gravity is actually the same everywhere, 9.8 meters per second squared down. All right, and because it's down often, we will be writing the acceleration due to gravity as like negative 9.8, right? Because again, down denotes that that's the negative. So to go negative 9.8 would be kind of like the same as going upwards then. All right. So writing it as positive 9.8 meters per second down is the same as writing it as negative 9.8 meters per second squared without having to say down then. So this negative is telling us that this acceleration is downwards. The acceleration due to gravity is used in the formula, change in velocity over time, when only the force of gravity is acting on an object. When using this formula, replace acceleration with this value right over here, or write this value right over here without using the word down then. When solving these types of problems, always indicate directions with a positive or negative in the calculations, and that's why I'm already preemptively saying this. If it's down, then make sure that you are adding that negative value right over there to denote that within the question, specifically even with these questions right over here dealing with acceleration due to gravity. So imagine that you have an egg that drops through a hole in the bottom of a nest. How far does it fall in 1 second? How far does it fall in 1 second? So I want you to even make a guess right now, write it maybe on the side of your paper here, what you actually think that's going to be. again, this is very, very useful to go ahead and do this. So if you want to, you hit having the wrong answer, that's okay. Then just do that in pencil. So you just throw up a value right over here. If it starts at a velocity of 0, so imagine that, right? Egg drops through a hole in the bottom of a nest. How far does it fall? So it's starting in the nest. It's going to fall down. We do know that acceleration that we just saw before is at negative 9.8 meters per second squared, or 9.8 meters per second squared down. So that means that it's an accelerating an object by 9.8 meters per second. So the velocity increases by 9.8 meters per second every second. So for example, after 1 second, you would have a velocity of 9.8 meters per second. After 1 second. After 2 seconds, your velocity would now be 19.6 meters per second. After 3 seconds, you get the idea. Then you're going to have your velocity increase even more. So for every second that egg is falling, it's going to have an increased velocity of 9.8 meters per second every second. That's what that's going to look like. So if you're dropping it for 1 second, that means in the end, your velocity is at 9.8 meters per second. So it's traveling 9.8 meters in a second, only at the very last moment of that second. So hopefully that begins to give you an idea as to what your displacement is. So write something down. All right, now that you've written something down, hopefully, what you should hopefully have done is written something down that is less than 9.8. So imagine that. It starts at 0, and at the very end, at the very, very end of that 1 second, it's now at 9.8 meters per second. So it starts off with a velocity of 0. At the very end of 1 second, it's at 9.8 meters per second. So if it was at 9.8 meters per second the entire time, well, then it would have traveled 9.8 meters within that 1 second. If it was at 0, resting in that nest the entire time, it would be at 0. The thing is, though, is it's increasing in velocity from 0 to 9.8 within that 1 second. So you might have even been able to do it in your head right now, what you believe this displacement is. So let's actually complete our TAD-VV this time and plug in the values that we do know. So we know acceleration is negative 9.8. We do know that we are dropping it, and it's going to take 1 second for it to fall and hit the ground or something. How far does it fall? We're going to be looking for a displacement. And we do know what our initial velocity is. If it just drops, it was initially at 0. I already told you what the final one is, and that's only based on the fact that we kind of thought it out, knowing what acceleration is, knowing that it's in the air for 1 second. But the reality is that it might not always be this easy. It might not always be exactly 1 second where we can kind of just figure it out. So in those particular cases, let's actually begin to work out what that actually looks like, all right? So we start off like this with our formula of acceleration is equal to the change in velocity over time. And we're going to rearrange this. And the reason being is because we want to actually figure out what our final velocity is first, so that we can then go and solve for our displacement. Because if you look back to one of those prior formulas on the other page, for example, what we notice is in order to figure out what our displacement is, we need to know these two values, the initial and the final velocity. And if we don't know the final velocity, we need to solve for that first. Then we can use the rest of the information. Because we know that our initial is 0, we know that our time is 1, and so then we can plug in the rest within this formula. But that's only after we find our final velocity. So let us do that first. If we're looking to find our change in velocity right over here, let's just rearrange this formula. We're going to have change in velocity by multiplying both sides by time. We're going to get acceleration times time. Now acceleration times time is going to be negative 9.8 multiplied by 1 second. And so our change in velocity is going to be negative 9.8. So that is the change in velocity right over there. And if we take a look, what is actually the change in velocity? Change in velocity, remember, is final value minus initial. And that is equal to negative 9.8. We do know what our initial is. We don't know what our final is. So our initial is 0, and so this actually cancels out. So this just becomes 0 right over there. And what you're left with is our final velocity is also negative 9.8 meters per second. So acceleration is negative 9.8 meters per second squared. Our final velocity is just negative 9.8 meters per second. So after 1 second, it's traveling at this velocity. So again, negative 9.8 or 9.8 meters per second down. Lastly, now that we have our final velocity, which we can plug in right over here, if we solve for this one, we can now look to solve for displacement. So we plug in our formula. It's never a bad idea to kind of write down what that is. And we're going to write it out this way. You could have written it out 2 ways. So we could have had it the average velocity times time. But remember, the average velocity times time is the same thing as your initial plus your final divided by 2 multiplied by a change in time. So it's going to be 0 plus negative 9.8 all divided by 2 and then multiplied by 1 second. So this divided by 2 is negative 4.9 times 1, still negative 4.9 meters. Have our units. This negative is actually telling us the direction right there. So we don't actually have to say up or down. This negative is already saying that we have actually, the egg is displaced 4.9 meters downwards due to this negative value right over there. So the negative does tell us, hey, we moved down. Lastly, we have an example with a girl throwing a baseball straight up in the air at 15 meters per second. What is the ball's velocity 2 seconds later? So again, I like to start off this way every single time. It allows me to stay organized and have our values. And so right off the bat, it's a gravity question, so I know my acceleration is negative 9.8. Throws a ball straight up at 15 meters per second. So our initial velocity is 15. It's going up, so it's positive. So I have a positive 15 meters per second. And what else do we know? 2 seconds later. So we have a time of 2 seconds. We do not really know anything else. We don't know what the final velocity is. It is not 0. Maybe it is 0, but we don't know that for sure, right? If it's 15 meters per second and it's doing this for two seconds right over here, and it's accelerating at 9.8, I have a good idea that my velocity is actually going to probably be negative, because look at this. After 2 seconds, that means there's a change in velocity of 19.6 meters per second. It started at 15, so it's going to be something like negative 4.6. So that is what my thought process is in my head, how I work it out there. Let's actually see what we end up getting here. So we're going to start it off in a very similar way here and say, okay, we first are going to need what our final velocity is. And we might not even need to find our displacement at all this time. We're just saying, what is the ball's velocity? What's the final velocity? So we're not going to need to solve for displacement in this instant right over here. So let's start by saying, well, what is our change in velocity? And we can actually use the formula from this previous one right over there. So we don't need to reinvent the wheel. If you have the formula right there, just use that one. So again, we're going to say, what's the change in velocity? It's equal to acceleration times time. Well, we have acceleration, we have time. So the change in velocity is equal to negative 9.8 multiplied by 2. And look at what is happening here. So what I verbally said is now coming true within the actual formula here. So thinking it through works, as well as actually using the formulas that are either given or that you can create based on other ones. So we had this initial one, acceleration is change in velocity over time. You can then use and manipulate this formula to get change in velocity is equal to acceleration multiplied by time. In the end, we get a change of velocity of negative 19.6 meters per second. With that, we can now go one step further, just like we did before, where we have our change in velocity is equal to our final velocity minus our initial velocity, equaling a negative 19.6. And now we just have to plug in the values that we do know. This time, our initial velocity is not 0, it's 15. And we can plug that in right over here. Or we can just go one step further with our values there, say our final velocity, add the initial onto the other side there, negative 19.6 plus our initial. That's going to be negative 19.6 plus what our initial is, which is 15. And if you add these things together, you will have negative 4.6 meters per second. We have our units, we have our direction, here's our direction, and we have our magnitude. So here's our final answer. And we also have our sig figs too. All right, that's a quick look at that. There's a lot more to this than just that. So we're just scratching the surface of what kinematics is and what it can all be. So we've only looked at a couple formulas today, uh, in addition to the ones that we have had in the past. So we looked at acceleration is equal to change in velocity. We looked at our displacement is equal to our average velocity times time. And then just kind of working out kind of little pieces here, as well as what I've asked you to do too, is to even just think, what do you think the answer is going to look like? What makes sense? Were you able to make a guess, something similar to this for your displacement? Or were you way off? You want to make guesses that are going to be close to what you calculate so that you can actually say, hey, did I get a correct answer? Does this actually make sense? And that's what we should really be thinking about, is be critical thinkers, not just plugging values into equations. You should think a little bit more about it. Imagine that you're this girl throwing this baseball at 15 meters per second. If you were doing that, you would be throwing it, well, even at times 4, that would be approximately 60 kilometers an hour. So a little bit less than 60 kilometers an hour, directly straight up into the air. And so you can imagine, okay, well, how far approximately would it go, or how long would it take before it starts coming down? Would it start falling after 2 seconds? And clearly the answer is yes, it would be, because we have a final velocity of negative 4.6. So it's actually on its way down, and it's still going to take a little bit longer to get all the way down, because the reality is this: it's going to hit the ground when our final velocity is, what do you think? Make a guess. If you had said negative 15 meters per second, you would be correct. So again, if there's no air resistance, no energy lost within the system, whatever it's going up at, so if it's going up at 15 meters per second, by the time it barely, just before it hits the ground, so the instant before it hits the ground, it'll be going at the opposite to that. It'll be going at negative 15 meters per second. So it'll be going down at 15 meters per second just before it hits the ground. And so we know that there's still a little bit more time left that it has in the air. And so there could be a lot more questions that could be asked with this too. We could be asking stuff like, well, how long before the baseball reaches the top? So if you were throwing it all the way up, how long before it reaches the height, the tallest portion? How high can the girl throw it, right? That could be a question. You could also ask, well, how long does it actually take to get all the way up here and then all the way back down? So what's the time that it takes to do that? So lots of types of questions that could be asked like that, right? So just be aware that you can take this in so many different directions, and we're going to be looking at more and more examples. The more examples you look, the less things that you're going to be surprised with later. So with that, good luck, have fun, and give it a try.